Hello everyone, my name is Jamila Pegues. I am a fifth-year graduate student now at Harvard University, where I study astronomy and computer science. And I am really excited to talk to you in particular, about a chunk of my PhD thesis, which has been to characterize young cool M stars and their planet-forming disks. So let's jump right into it. So, protoplanetary disks are precursors to planetary systems like our own solar system, and I'm particularly interested in disks around M stars, and that's because disks around M stars tell us about the most common forms of planet formation in our local galaxy. Now, disks are pretty useful tools for a number of reasons. For one, we can use the Keplerian rotation of these disks to actually put precise constraints on the stellar masses at the centers of these disks. And that's great because stellar mass is so important for understanding and mapping out stellar evolution. More generally, these disks are full of interesting chemistry, and if we understand that chemistry, we understand the chemistry that's involved in the most common forms of planet formation around these stars. Okay, so in this talk, we're going to use a sample of protoplanetary disks to do exactly those two tasks that I just talked about. There are a total of 5 disks in our sample around M4 to M5 type stars, and the stars are pretty young, pretty dim, and of pretty low mass. And here I'm showing the disk continuum for our sample, which at this resolution appears to be pretty smooth. Now, the first question we wanted to answer was, do we detect any interesting chemistry in disks around M4 to M5 stars? And the answer is yes, we do detect interesting chemistry. So here I'm showing in each column a different disk, and each row is for a different molecular line. And we detect all of the CO isotopologues within our sample towards all 5 disks. We also detect C2H and HCN towards all 5 disks, and we detect the fainter lines of DCN and H2CO towards a smaller subset. Now, what's interesting about this interesting chemistry is that we detect these same sorts of lines towards disks around solar-type stars. So bear that in mind. We'll circle back around to that towards the end of this talk. Okay. Now, the first thing we're going to do today with this talk is use the brightest emission, the CO emission, to actually measure dynamically the stellar masses at the centers of these disks. Now, for this measurement, we're able to use 12 CO and 13 CO emission observed towards 3 disks, for which we're able to resolve that nice double-peaked structure in the spectrum, which indicates the underlying Keplerian rotation. To do these measurements, we'll use the code Diskjockey. It's on GitHub. Feel free to go check it out. It's pretty cool. And here are our results. So along the x-axis, we're showing each disk or star plus disk system, and the y-axis shows the dynamical mass measurements for 12 CO in purple and 13 CO in blue. And we can see that for 2 of these star plus disk systems, the 12 CO and 13 CO results are pretty consistent with each other. For the third system, J1100, we actually had really high uncertainties on the stellar mass, simply because of the disk's low inclination angle. And for these dynamical mass measurements, the stellar mass is actually highly correlated with inclination angle, so that a low angle naturally translates into high uncertainties. But hey, we do what we can with the data that we have, as always. So how do these dynamical mass measurements compare to the masses that we would have predicted using fiducial, our non-magnetic stellar evolutionary models, given our assumptions of these stars' effective temperatures and luminosities? Let's make that comparison. In the plot on the right, we're comparing fiducial stellar evolutionary model predictions along the x-axis to dynamical mass measurements along the y-axis. The dark purple points are stars from this work, while the pale pluses are stars from a compilation of dynamical masses from 2019. Now, ideally, all points would fall along the thick black line, or the 1-to-1 ratio, which would indicate that these models are correctly predicting the dynamical masses. But instead, we see that these fiducial models are actually underpredicting the dynamical masses by 25% or more. So what could be causing these discrepancies between our predictions and our measurements? Well, there are a couple of possible different options, but for this talk we'll focus on one, which is that maybe these fiducial models don't incorporate enough physics to really represent our low-mass stars. So let's try stellar evolutionary models with star spots. We'll be using tracks from the aptly named spots code released earlier this year. Now these tracks have this parameter f spot, which represents the fractional star spot coverage on the stars. Now star spots on a star can indicate underlying magnetic activity. So by varying this parameter f spot, we're essentially parametrically varying the magnetic activity for the stars in our sample. And so we use these tracks for the stars in our sample and also for the stars from the aforementioned 2019 compilation to try to find the value of f-spot, the fractional spot coverage, that best reproduces the dynamical mass measurements. And here are the results from that work. So along the x-axis, we have the assumed effective temperatures for these stars, while the y-axis gives the interpolated value of f-spot that best represents the dynamical mass measurements. And it's interpolated simply because the output tracks from the spots code are discrete. Now you'll notice that first off, these stellar evolutionary models with star spots are capable of reproducing the dynamical mass measurements for these stars, and that's awesome. There might even be a trend between f-spot and effective temperature, although it's hard to say for sure given the wide constraints that we have on the effective temperatures for each of these stars. So to possibly make this trend more quantitative rather than just qualitative, we could really use future work in this area. For one, we would need more dynamical mass measurements of low-mass stars to fill in more of this plot, and we would also need tighter constraints on the effective temperatures for these different stars. So, we've talked a lot about the stars at the centers of these disks. Now let's back out and talk about the chemistry in the disks around these stars. As a reminder, this is our full sample, and notice that we have corrected the stellar mass bracket given our new results from the dynamical mass measurements. So we want to use the disk chemistry in our sample to try to answer a few questions. But before we start making these wild comparisons, let's take a moment to put our sample in context. These plots compare populations of disks in terms of their stellar mass along the x-axis and their dust continuum fluxes on the left plot and C18O fluxes on the right plot along the y-axis. Now the dark gold circles are the M4-M5 disks from this work, while the white squares and white pluses are solar type and Herbig A disks from previous works that have been observed in the same sort of chemistry that was observed for our own sample. And as you can see, overall our sample fits in quite nicely, and we can start making these comparisons. Okay, so now that we've justified making these comparisons, we'll use a few different chemical tools to actually investigate these questions. Let's start with excitation conditions. For the biggest, brightest, and boldest disk in our sample, J1100, we were able to use fits to the hyperfine structure of C2H and HCN to actually measure excitation temperatures, optical depths, and column densities. And that's exactly what we did here. So we made these measurements interior to the dust continuum, where sufficient signal-to-noise actually existed, and we found that generally C2H and HCN are both pretty cold, but HCN is slightly warmer, that HCN is more optically thick, and that C2H has higher column densities. What's interesting is that these same sort of excitation conditions were found for solar-type disks in previous works. So go ahead and put a little check in our comparisons between M4 and M5 disks and solar-type disks. Now the second thing we'll investigate in this talk are flux ratios, and we'll focus on one flux ratio in particular, which is C2H versus HCN. So this plot shows HCN fluxes along the x-axis, all scaled to 140 parsecs, versus C2H fluxes along the y-axis, similarly scaled. The dark gold circles are again the M4 and M5 disks from this work, while the white squares and white pluses are the mainly solar-type disk sample from previous works. As you can see, the C2H versus HCN line fluxes are pretty correlated, and that same sort of pattern seen for the solar-type disks appears to extend towards the M4 M5 disk sample. So put another check in that checkbox comparison between solar-type disks and M4 M5 disks. Now we can take this a step further and see how different flux ratios vary with stellar mass across these different samples of disks. So the x-axis and the y-axis give the stellar mass and flux ratio respectively, and the flux ratios are written within each subplot. And if you let your eyes scan over these different subplots, you'll see, well, there's not too much to say, right? There's no clear trend on these ratios with stellar mass. And this may imply altogether that these disks around these two different types of stars might have similar patterns of underlying chemistry, at least in the disk regions where these observations and measurements are most sensitive. Now the last thing we'll investigate in today's talk are disk average column densities across the entire sample. And we do this measurement by assuming a range of excitation temperatures and optical depths for the different disks. And that's what we're showing with this plot here. So the x-axis gives the disk, while the y-axis gives the disk averaged C2H versus HCN column density ratio. The clusters of stars and bars each assume the excitation temperatures and optical depths that are written along the bottom left of this plot. Finally, the horizontal dark line and shaded region span the 16th, median, and 84th quartile estimates of this ratio from a sample of mostly solar-type disks from the literature. Now you'll notice that the median values for our sample of important M5 disks actually exceed even the 84th quartile estimate for that sample of mostly solar-type disks from the literature. So that implies that this ratio is enhanced within our M4 M5 disks of our sample. And that's actually consistent with what has been seen in the inner disks of low-mass M stars. Now this study from 2013 compared C2H2 versus HCN fluxes and column densities for T-Tauri disks, shown here in black, versus low-mass M-star and brown dwarf disks, shown here in red. And they found that C2H2 was enhanced relative to HCN for those low-mass M-star and brown dwarf disks. Now this study was an infrared study, which means that it was sensitive to the inner 10 AU or so of these disks. So if we couple that with our results from this work, using millimeter observations, we find evidence of these enhancements in different regions of these disks. Now, are these enhancements caused by the same underlying chemical processes? Not necessarily. We would really need modeling to tease out that additional layer of this analysis. So stay tuned. Now, a caveat, in making these measurements, we did assume that C2H and HCN emission are coming from the same or similar layers in the disk regions where these observations are most sensitive. Now again, we will need modeling to really tease out where this emission is coming from. So again, stay tuned. All right, and with that, I'll leave up this little takeaway slide. Thanks so much for stopping by this pre-recorded talk, and I hope you enjoy the rest of the conference. Thank you.